Ha ha! Nothing like a bit of black pudding to get you going in the morning. Kings of Sheffield. Why was Sheffield king of the steel and cutlery business?
The answer to that question is location, location, location. Sheffield is surrounded by hills and valleys rich in coal and iron ore. Water running off the hills could provide power, and there was a network of navigable rivers that could ship materials in and out.
I'm on Comrade, one of only 2 surviving Humber keels restored to sail. Keel, kiol, is an Anglo-Saxon word meaning ship, and ships like this have been trading on the East Coast and with Northern Europe and the Baltic since before Anglo-Saxon times. And that trade has been very important to the development of industry in Sheffield.
Trade with Sweden would prove particularly significant. Iron was the main industry in the Sheffield area for centuries. But about 300 years ago, small amounts of a new material were imported to give tools a cutting edge. Swedish steel.
So what's so special about steel? Cast iron, wrought iron and steel look pretty much the same. However, utilising this microscope, we can have a look at their structures. Bearing in mind that the early steelmakers had no idea about what the crystalline structures were of these materials, they just knew that if they added carbon, they changed the nature of this material. So, cast iron looks like this. It has a very open crystalline structure. All those little black bits, the graphite, make it weak. It's good under compression, but under tension, no good at all, and it can't take any shock loading. Wrought iron looks like this. You can see where the structure has been stratified by heating and hammering, annealing. And steel looks like this. You can see it has a much more uniform structure. It looks stronger, and it is. It's got the best of both worlds, strength and shock resistance. Good stuff. So, steel is strong, under pressure, it's flexible, and you can sharpen it.
Iron, charcoal and coal to heat your furnace, all you need to make steel. You'd think Sheffield was in business. No. Local iron ore had too high a phosphorus content for the early methods of steel making. But never mind, we'll still make our own steel, we'll just have to import our iron from Sweden. By 1700, crude steel was being made in Sheffield in cementation furnaces. Swedish iron and local charcoal were placed in a chest and heated for a week. The outside of the iron blistered. These blisters were a carbon and iron alloy, blister steel.
The abundance of water in Sheffield not only meant that large vessels could bring raw materials in and take finished goods out, it also meant power to turn water wheels. In the 17th and 18th centuries, Sheffield had over 160 mills. At this site in Abbeydale, there were 4. In the 1740s, a clockmaker, Benjamin Huntsman, wanted better quality steel for his precision instruments and clock springs. He came here to Sheffield with a new method of smelting blister steel in clay crucibles. His was a more efficient and controllable method of producing quality steel. He could produce 25 kilograms in only 4 hours.
It was a crucial breakthrough. Making steel fast would make Sheffield king of cutlery.
In the 1740s, Huntsman's process was introduced here by the Tyzack family. Every part of the process is grouped round this central courtyard. It's quite different from cottage industry in the village smithy. It's a self-contained, water-powered steel and scythe works. Here we have the pot shop, the charge room, the teaming bay and the furnace. This is the tilt hammer forge and the grinding hull. The first step in the process is to make the pots or crucibles. Reminds me of being at Weston-super-Mare as a child. So for about 4 or 5 hours, the potman will get the clay to the right consistency. There's fire clay in here, china clay, coke dust. That'll do. The clay was needed not just to mix it, but also to remove air bubbles. Because if you're using a crucible to heat molten metal, you don't want air pockets in it because it'll explode. So, the right amount was weighed out by the potman, who would then put it into this mould. Then you put this plug in, hammer it down, and you end up with a crucible inside the mould. Take the plug out, then turn it over, knock it out, and bring it over here, carefully, because it's still soft. Past the fire, which wasn't there to keep them warm, it was to make sure that they dried out. The crucible was then fired in an annealing oven before being taken up to the charge room. And I would then shut the door, because this next part of the process was a secret. The crucible process was a refining process. So we started off with the raw material, blister steel. There are the blisters. I used Swedish bar iron because it was purer than British. There was less phosphorus in it. So first of all, on this anvil, supported by this tree trunk that goes right down to the ground floor, we break up the blister steel by hand. So I take my blister steel and other weighed ingredients, including limestone, to act as a flux, bringing the impurities to the surface, put them all in my charging pan. Charge would have weighed around 25 kilograms, and I put all that into a crucible. Then the crucible containing the 25 kilogram charge would have been lowered into the furnace, each one taking 2 crucibles. The lid would have been closed and the temperature raised to 1550 degrees centigrade. Then after 3 or 4 hours, the lid would have been opened, and then the puller out would wrap his lower body in water-soaked cloth, a water-soaked leather apron, position himself over the furnace, not a pleasant job, and the crucible would have been pulled out. Right, I have to work very quickly now because we're dealing with molten metal. The 2 halves of the ingot mould, like this, were clamped together, placed in a pit. Then the top was taken off the crucible, and then it was teamed in, poured in. The idea was to get it in quickly without touching the sides, which made a perfect ingot. The next stage of the process happens here, in the tilt hammer forge. Now, to work metal by hammer, you have to have it hot. And to heat it up to the proper temperature, you need a blast of air. The blacksmith did it with the bellows, but here, the water wheel does the work. Right, I've had my steel ingot rolled out at my mate's rolling mill up the road, and I've now got a piece about the right size to start making a scythe. So I'm going to reheat that. Now, just a word about scythes. Seems quaint now, the idea of a scythe, something you find on the wall of a pub for decoration. But remember, pre-mechanisation, the scythe cut every single ear of corn. So, no scythe, no bread. It was the most important agricultural tool. It is on the Russian flag. So, after heating up again, I bring my steel bar over here to the hammer, and they work like this. The water wheel at the end of this shaft turns a cogwheel, and these connect intermittently with the head of the hammer, so it drops it, bang, bang, gravity doing most of the work. It also works the other way, catching the back, bang, 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 like that. Simple. The vibrations from these hammers could be felt in the nearby houses, and it was so great in here that whoever was working at them had to be suspended from the ceiling in order to stop vibration. So after roughly shaping on the main hammer, the strips of steel were combined with wrought iron for cost purposes, and then with this hammering at 6 times per second, you would shape your scythe. The sandwich was reheated and worked under the plating hammer, constantly drawing out the steel in the centre to provide the edge. That looks more like it, doesn't it? Then this was hardened and tempered and worked on an anvil, and then it was ready for the grinding shop. There were originally 6 of these grinding wheels in here, all made from local sandstone, each one of them about 1.83 metres in height, weighing 2 tons each, and they were all powered by one water wheel. Arthur Young noted in the 1770s that grinders were highly paid, 18 to 20 shillings a week, because their work was dangerous. The velocity of the grindstones was so fierce that if they should break and fly off, they would often kill the men working on them. And this is what grinding's all about. Precision work next to the wheel. All right, Peter?
Okay.
But the greatest danger to the grinders was silicosis from the fine metal dust and stone dust. Look at all that. And that's just 1 year's work. Good stuff, this steel. You can get a proper edge on it. You can make money out of that, which of course they did. I bet there's loads of other stuff you could do with it. Sheffield not only had large supplies of iron, coal and water, it now also had the steel industry, which was ideally placed to exploit the steam engine. And one steam engine could drive 100 grindstones and the bellows for the furnaces.
Increased demand for steel and its raw materials coal and iron led to improvements to the waterways. The air and coal navigation had been constantly improved since 1699. To cope with this demand, an inland port, Goole, had been built on the canal. In 1836, the chief engineer, William Bartholomew, introduced steam tugs, and they could each pull 10 keels.
And then, in 1863, Bartholomew came up with this, a unique compartment system. Using steam tugs to tow keels, which were designed to sail independently, was inefficient. So Bartholomew invented this. Each one of these pans can carry 40 tons. They're then connected, almost like wagons in a train, and this is actually called a train. There would have been 19 usually, all designed to work together. This false bow here, the Jeebus, was designed because Bartholomew originally envisaged the pans being pushed. Not very good physics. So after experimentation, this is what happened. The tug pulls them. They're not going very straight. And that gave rise to their name. These are called Tom puddings. Tom meaning big, and pudding as in black pudding. It's like a big line of wobbly sausages. Imagine 19 of them. Not an easy job. That is the best bit of the system. That is a boat hoist. That could hoist each one of those pans, one of those Tom puddings, up hydraulically and empty its contents into a waiting coastal collier. It was a true compartment system. This is Goff, who used to work this system when it was operational. When did he finish, Goff?
About 15 years ago.
So it was working until 15 years ago.
About 100 years. Not bad. He wasn't on it for all that time, like. Each hydraulic hoist had to lift one of these pans, or tom puddings, about 12 tonnes, its load of coal, between 38 and 40 tonnes, and the cradle on which it was held, about 70 tonnes in total. I'm going to use muscle power, such as it is, but originally there would have been a powered capstan to pull the compartment boats that have been lined up, ready, beneath the hoist. Right, the loaded compartment boat is now directly over the cradle. Here, two men would have clamped it in position either side and then rowed with the cradle as it lifted the boat and the coal 11 metres into the air. And then, above me, in a raised position now, was the coal chute, which was lowered. The spoutman, who travelled 11 metres on the cage, could then control the rate of loading of the coaster, which would have been right here, next to the hoist. Up and in. Simple. Eventually, there were 5 of those hoists, and this successful system ran for over 100 years. Thousands of compartments carrying millions of tonnes of coal. As late as 1979, there were over 300 compartments shifting 200,000 tonnes of coal a year. And the steam tugs were replaced by diesel tugs. In 1800, Britain was producing 3,000 tonnes of steel a year. But very soon, demand was outstripping supply. Everybody wanted steel for their engineering, the expanding railways, the shipbuilding, the larger tugs. The problem was eventually solved in 1856, when Henry Bessemer invented a process for producing mass-produced steel. This giant machine is a Bessemer converter. It can convert 25 tonnes of molten iron to steel in 20 minutes. In 1855, Bessemer experimented with a vertical converter, but in 1860 he patented this, the fast-acting tilting converter. This was the breakthrough Sheffield had been waiting for. The Bessemer process could convert high phosphorus local iron ore into steel. No more need for Swedish iron. Sheffield was poised to become king of steel.
The bowl is tilted down and low-grade molten pig iron is poured in through the mouth, then swung back to vertical, and a blast of air is blown through the base of the converter, through the liquid metal. The low-grade iron is high in carbon and the hot air burns off the excess carbon. A spectacular 10-metre flame and fountain of gases shoot out of the mouth. When the iron is purified, the bowl is tilted down again and the newly made steel teamed or poured out into ladles and cast into ingot moulds. Bessemer steel was an engineer's dream. A material for everyday use stronger than iron. And within 20 years, Sheffield alone was producing 10,000 tonnes of Bessemer steel a week. That was a quarter of the UK output. It was used for machinery, for railways, for household goods, everything. This is a piece of armour plate from the first ever armour-clad battleship, HMS Warrior, 1860. It's rolled. It's very thick. And it started Sheffield's association with battleships. And if you're making battleship armour plate, you probably need something quite large to roll it out. Something round about the size of this. It was time for steam, steel and ships to come together. I think it's really fascinating that this engine is around the same size as those in the Titanic. Only they were namby-pamby triple expansion engines, only developing 7,000 horsepower each. This 12,000 horsepower monster uses 3 high-pressure cylinders in line. It's like a sports car engine. Everything about this engine is massive. It was built by Davy Brothers of Sheffield in 1905, and there were 4 of them built at the same time. One went to Camels, this one, to roll armour plate. Another one went to James Brown's for the same purpose. Another one went to the Japanese government. And one, destination unknown. One of these engines is missing. The power of this engine is immense, 12,000 horsepower. It could turn a 50-ton ingot of steel into a piece of armour plating 40 centimetres thick. The key to producing armour plate was that the ingot had to go backwards and forwards through the rolling mills. And this engine can reverse, this entire huge monstrosity can reverse in 2 seconds using this Joy reversing gear.
In the late 1970s, this amazing machine finished its working life rolling stainless steel thermal shields for Calder Hall Nuclear Power Station.
Blimey. It was an aspect of the steel industry that was to grow to epic proportions. So much so that by the beginning of the 20th century, Sheffield was known as the arsenal of the world.
From master cutler to major steel producer, for over 200 years, Sheffield was the king.
William Cobbett, 1830. All along from Leeds to Sheffield it is coal and iron. Nature has laid the beds of iron and the beds of coal alongside each other, and art has taught man to make one work upon another. Whatever other nations may do with cotton and wool, they will never equal England in regard to things made of iron and steel.
In the next episode, I'll be looking at how the Welsh coal and iron industry spurred on developments in steam transport.
Of all the boats we've used on this series, this is the one that I most covet. Please can I have one of these when I'm grown up?